Hello, this is Jack Jackson. In this video, we're going to be putting together several ideas that we've been talking about in this unit to talk about Maclaurin and Taylor series. So earlier we computed Taylor polynomials to approximate a function. So remember that we found that the following approximation of a function f with its nth degree Taylor polynomial centered at a. So f of, let me go ahead and just say this. So our function f of x was approximated by this nth degree Taylor polynomial p sub n of x, which was f of a plus the sum from k equals 1 to n of the kth derivative of an a of, divided by k factorial times x minus a to the k. And sum there goes from k equals 1 to n. So there's actually, counting the constant term, there's n plus 1 terms there. An nth degree Taylor polynomial centered at a. Now, this polynomial gives an approximation for f of x. So f of x is approximately p sub n of x as long as x is reasonably close to the center point x equals a. And of course, we knew that we could let x deviate from a little bit more if we could get that power to go up higher, or even if we leave it at a specific spot for x, then the bigger that power was, the bigger the degree was, the better it approximate that function. Okay. Of course, they all approximate it perfectly at x equals a. So it seems to reason that if we just do more and more and more and more and more of these terms, we'll get a better and better approximation. And in fact, what would happen if we did infinitely many of these terms? Well, now we have a Taylor series. And that's what we want to look at in this particular section. So our Taylor series now is f of a plus the sum from k equals 1 to infinity of f, the kth derivative of f evaluated a divided by k factorial times x minus a to the k, and sum from k equals 1 to infinity again. So this is an infinitely many terms Taylor polynomial. So it's a Taylor, not polynomial anymore, but a Taylor series, power series. Okay. So we have to know, one of the things that we learned from the last couple of videos is we need to be careful to determine the domain, also known as the interval of convergence, for the power series. And so we will use maybe some ratio tests and some other tests to determine that interval of convergence. And we hope that this actually is equal to our function f of x. Maybe on a possibly smaller domain than the original function has. However, this may not be the case. So in order to determine that the series actually converges to the original series for inputs within its interval of convergence, we need to show that the remainder term approaches zero. So putting this together yields the following theorem. And the left side is what we already know for Taylor polynomials, and the right side is extending this to Taylor series. So here's what we have here. We'd have a function f that's differentiable through order n plus 1 in an interval I containing x. Then for each x and I, there exists a z between x and a such that f of x is p sub n of x plus r sub n of x. What's p sub n? P sub n is the sum from k equals 0 to n of f, the kth derivative of f evaluated at a over k factorial times x minus a to the k. Here we're assuming that when you let k equal 0, this is just the 0th derivative is the function evaluated at a, and that x minus a is to the 0 is 1 even when x equals a. So if you assume that, then that's correct. And then the remainder is how far this is off from the original function. And the Taylor's theorem says, well, it's off by this amount. You go to the next term, this goes up to n, the remainder n, you go up to one more term, the n plus 1 term, which would be x minus a to the n plus 1 over n plus 1 factorial, and then you do the nth derivative, the n plus 1th derivative of f, evaluated at z, where z is some number between wherever x is and a is. Okay, so z is unknown, so it's a little bit hard to know exactly what this is, but so often you can get a bound on it because you can say, well, this derivative is no bigger than something. Okay, so that's just sort of on the polynomial side. Now on the series side, if we have f of x is sort of your p infinity of x, you know, your infinite series, okay, power series, it's the same thing. It's the kth derivative at a divided by k factorial, x minus a to the k, and then you take sum that from k equals 0 to infinity. This needs to have infinitely many derivatives, not just through n minus 1. Okay, and this is if and only if what? That remainder term, this right here, approaches 0. Now, Maclaurin series is just a Taylor series centered at x equals a is 0. Centered at 0 is a Maclaurin series. So this x minus 0 just becomes x to the power k. Okay, and so this is, and of course you're evaluating at 0 too. So this is all the derivatives evaluated at 0. The kth derivative evaluated at 0 divided by k factorial times x to the k. Sum that from k equals 0 to infinity, and you got a power series centered at 0. And this is going to be specifically what's called a Maclaurin series. Now, infinite series of these types were studied by lots of mathematicians, even from back the guys that started out with calculus, Newton and Leibniz, also the Bernoulli family, Gregory de Moivre, Maclaurin, and Taylor. Maclaurin series are actually named after Colin Maclaurin. He lived from 1698 to 1746. He was a Scottish mathematician, and he was the first to clearly lay out Newtonian calculus for a broader audience. So he was the first one to really try to write careful treatise for the Newtonian approach to calculus so that folks could learn from it. And he actually had the key ideas of series and really probably deserves the greater credit than Taylor. Taylor series are named by Brooke Taylor, 1685 to 1731, who also is famous for discovering integration by parts. And so these two guys kind of together, well, all of these guys really kind of come up with some of this stuff about series that we've been studying. And Taylor series are named after Taylor, even though probably Maclaurin had probably more of the idea behind it. So let's directly use Taylor's theorem to derive some series representations for a few standard functions. And we can use exactly the same approach that we use for Taylor polynomials. However, in order to extend this method out to infinitely many terms, we have to be able to find a clearly discernible pattern for the nth derivative of the original function that's going to continue on forever. And let's start with one of the most important Maclaurin series, the series expansion for f of x equals e to the x. Now this one is kind of easy in a way because all the higher order derivatives are identical with the original function. The derivative of e to the x is e to the x, so the second derivative of e to the x is e to the x, and the third derivative of e to the x is e to the x, and so forth. So that makes this one pretty easy to work out. So the nth derivative of x of the function e to the x is e to the x. And when you evaluate that 0, e to the 0 is just 1. So the series for e to the x is just a sum from k equals 0 to infinity of 1 over k squared x to the k. So that's 1 plus x plus 1 over 2 factorial x squared, so that's 1/2 x squared, plus 1 over 3 factorial x cubed, that's 1/6 x cubed, and so forth. So there it is written out a couple of different ways there. Okay. So very simple series in one sense, follows very directly from Taylor's theorem. So there's the Maclaurin series for e to the x. So in order to verify this is actually an equality, that the Maclaurin series actually converges to f of x e to the x, we need to show that the remainder term approaches 0. So the remainder term looks like this. It is the nth plus 1th derivative of z over n plus 1 factorial x minus a to the n plus 1. And we want to see what happens with that. Well, this derivative is e to the z, and we take the limit as n goes to infinity. This factorial is going to dominate over this exponential, so that goes to 0. Okay, so let's see what we got now. Okay, let's determine an interval of convergence for this series. Well, let's do the ratio test. So within this interval of convergence, in the domain of this series, it should be equal to the original function. So as always, we get the k plus 1 term over the k term. This part here cancels out. It just leaves you absolute value of x. This is k factorial over k plus 1 factorial. That cancels out, leaving k plus 1. The limit of that is actually just 0. And so that means this converges no matter what. So this converges for all real values. And so the series converges absolutely. And we've seen that it converges to e to the x because that remainder term approaches 0. So for any real number x that we put in, e to the x is equal to this power series representation. So with this in hindsight, some mathematicians like to take this as actually the definition of the exponential function. And of course, we can use this to find e to any particular number of digits by just working this out enough terms of this polynomial, or e to any power for that matter, we can work out using this. And so if you remember earlier in an earlier video, we looked at the first 6 terms of this, the 5th degree polynomial, this from 1 up to this x to the 5th term. And we plugged in, say 1 for x, and we worked out e correct to 4 significant digits using that. So let's see if you can work out this next one. Use Taylor's theorem to find Maclaurin series expansion for f of x equals sine of x. Determine the interval of convergence for the series and prove that it converges to the original function. Remember, Maclaurin series is just a Taylor series centered at 0. Work this out yourself. Press pause now. Well, the key is going to be looking at the derivatives, right? So we start with f of x equals sine x. The derivative of sine x is cosine x. Derivative of cosine x is negative sine x. Derivative of that is minus cosine x. And the derivative of that is back to sine x. So by the time you get to the 4th derivative, you're back to the beginning. So we have a 4-function cyclic pattern. Here's this one. Sine x is the 4th derivative. Cosine x is the 5th derivative. Minus sin x is the 6th derivative. 7th derivative is minus cosine of x. And then the 8th derivative is back up to sine x. Then the 9th derivative, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th, 19th. They just go in a cycle there. So one way we could say this is if x is congruent to 0 mod 4, and remember that means that when you divide x by 4, the remainder is 0, then you're going to get this first one. It's all the multiples of 4. The 0th derivative, the original function, the 4th derivative, the 8th, 12th, 16th, 20th, and so forth. Derivatives are all sine of x. Now, if x is congruent to 1 mod 4, that means you take x, divide by 4, you get a remainder of 1, so that would be like 1, 5, 9. So the 1st, 5th, 9th, 13th, 15th, 13th, 17th, and so forth derivative are all cosine of x. If x is congruent to 2 mod 4, take x, divide by 4, and get a remainder of 2. You get minus sine x, so that would be like the 2nd one, and the 6th one, and the 10th one, and so forth. Or if x is congruent to 3 mod 4, take x, divide by 4, remainder 3, then you're going to get this last one of minus cosine x. You get this pattern. Now, of course, we don't really care about what those things are as much as we do as what they are when they're evaluated at 0. So we plug that in. Remember, sine of 0 is 0, cosine of 0 is 1. So that first one, sine of 0 is 1, sine of 0 is 0, cosine of 0 is 1, sine of 0 is 0 again, opposite of 0 is still 0, so that's 0 for that one. And cosine of 0 is 1, so that one's minus 1 for the end. So notice that the even ones, when x is congruent to 0 mod 4 or 2 mod 4, that's the even numbers, then those will all have a 0 for that. So those terms are just going to disappear. So there's not going to be any even number terms they're all going to just be 0. So we're going to be just left with the odd terms, and they're just going to alternate in sign, bouncing back and forth between 1 and -1. And so we end up with this pattern here. We get, let's just work it out here on the right first. We get this pattern right here is what we end up with. So remember, there's all the even terms are not there. So all we get is the odd power terms, 1, 3, 5, 7, 9, 11. The coefficients are just 1 or -1 from this part, but they still have that 1 over k factorial. So here we have, whatever the power is, we have a factorial in the denominator. So it's a 1/3, 3, x to the 3 is a 1 over 3 factorial. The x to the 5th is a 1 over 5 factorial. But we also have an alternating sign because of this thing here. So every other one is going to switch back from positive to negative. So when the power is 1, 1's congruent to 1 mod 4, so we get a positive there. But then we go to 3, 3 is congruent to 3 mod 4, so we get a -1 there. So these are going to alternate, plus, minus, plus, minus, plus, minus. Now another way to see this, of course, is to go ahead and multiply these things out in the bottom, which I've done a few terms here. But you can also see this as a pattern here that we can write down. So the alternating sign part, let's see, starts with 1, then goes negative, positive, negative, positive, negative. So that can be just -1 to the k. If we start at k equals 0, that will start with a positive, okay? We only want odd powers, okay? How do you get an odd number? Well, let's think about this a minute. If you have x is any natural number, that's going to be all the natural numbers, or all the whole numbers, I guess. We start at 0. Okay, if you have 2 times k, that's going to be all the even numbers, 2, 4, 6, 8. Well, if we add 1 to that, that's going to start at, and we start k at 0, that's going to start at 1, and then we're going to get the odd numbers. So if you plug in k equals 0, 2 times 0 plus 1 is 1. Add 1 more, k is 1. 2 times 1 is 2, plus 1 is 3. K is 2. We go here. So there's k is 0, 1, 2, 3, 4, 5, gives us a power of 1, 3, 5, 7, 9, 11. So remember that with linear functions, this is going to start at, when x is, or k is 0, this is going to start at 1, and it's going to go up by 2's. So it's going to get all the odd numbers, 1, 3, 5, 7. Okay, and then the bottom down here is just take that power, put a factorial over it down here in the bottom of the fraction. And so there's how we could write it as a summation form. Here's written out the first few terms, and then this is, expanding out what those factorials are. So now what's the domain of this particular one? Well, take that thing right there, do the ratio test. Put that in the bottom, put it in the top, and replace the k's by k plus 1. That goes there, k plus 1. 2 parentheses k plus 1 plus 1. 2 parentheses k plus 1. So be sure you put the parentheses there and work this out. So now we got a little distributing to do here. 2k plus 2 plus 1 more is 2k plus 3. So that's the power on the x here. Power on the x here is 2k plus 1. All right, this one goes to the bottom down here. This is 2k plus 2 plus 1 more is 2k plus 3, and then it's factorial. So that goes to the bottom. This is going to flip up to the top and be 2k plus 1 factorial. And the negatives, they actually cancel out to always be -1, but then the absolute value is going to take care of that, so we can just get rid of that part. Now let's see if we can do some simplifying here. Subtract exponents here. 2k plus 3 minus a 2k plus 1 is 2k minus 2k is 0. 3 minus 1 is 2. So we get an x. There's 2 more x's in the top than the bottom. So we're left with an x squared. Absolute value of x squared is x squared. Bring that out front of the limit because it doesn't have any k's in it. All right, 2k plus 3 factorial is 2k plus 3 times 2k plus 2 times 2k plus 1 factorial. Well, the 2k plus 1 factorial cancels with that part right there. Leaves the 2k plus 3 and the 2k plus 2 left over. Everything else has been factored out or canceled out, so we just left with a 1 at the top. That limit is 0. No matter what x is, that limit is 0. So that's the good news. This is the best kind. This one actually converges for all real numbers x, so this is an appropriate series for all real numbers. does it actually converge to the sine function? To prove that, we have to look at the remainder term, which is the n plus 1 derivative evaluated as z over 2n plus 1 factorial x minus a to the 2n plus 1. Take the limit as n goes to infinity of that absolute value. A is 0, so this is just x to the 2n plus 1. This is, for fixed x, this is a fixed number right here. Well, it's a fixed number to a power. This is, this derivative is no bigger than 1, right, in absolute value, right? This is because it's a sine or a cosine, plus or minus, and both of those only go between 1 and -1. So this nth derivative evaluated anywhere, really, is always between 1 and -1. So its absolute value is between 0 and 1. So this is less than or equal to just put the 1 there. And this factorial is going to dominate over this power function. So, so now remember, we're thinking of x as a constant, n as the variable. And so this is going to go to 0. And so we see that since that's 0 all the time, this does actually converge. And so this gives us an alternative way, exact way, of representing a basic sine function for all real numbers. Sine of x is a sum from k equals 0 to infinity of -1 to the k over 2k plus 1 factorial times x to the 2k plus 1. That's x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th and so forth. You got to see some of those terms worked out there. So one thing we need to note is talk about this convergence. The series converges to sine of x for every real input for x. Therefore, if we use enough terms of this series, of the finite series, a Taylor polynomial centered at 0, it will approximate sine x for any input for x. However, since this is centered in 0, although we'll only take a few terms to approximate sine of x very well for x values close to 0, it may take an extremely large number of terms to approximate sine of x for x values that are far from 0. If we want to use a polynomial approximation, or the first part of the power series, for sine of x, then we should be sure to center it up at an x value close to the x value that we want to find out. Okay, I have several more examples I want to do, but I think this video has gone on long enough. Let's stop here and we'll come back and do some more examples of this in the next video.